so that we're able to save on a
Okay,
little bandwidth.
okay. That's fine.
Perfect. So another thing I should mention, since the topic of this conference is numerical relativity, is that I believe on March 22nd is the date. We're planning to have a colloquium, which will be recorded so that people can watch after the fact online, where some of the developers of the both the exact package and then many of the packages built on top of that will be discussing their process in developing that and some recent work and things that they've been doing. And so I would be remiss if I didn't mention that that's an upcoming event that we will be hosting online, and registration is completely open. So if you happen to be available to watch it live, there'll be questions and answers sessions during this as well. If you cannot attend live, then by all means, please register, and then you can watch the recordings after the fact. So I can make sure that the information when we have the page for this is sent so that everyone can take a look at that, because that's another very definitely exciting. In fact, we were exciting to see that there were 2 talks featuring exact and related packages here at this very conference. So that's great. It's always a pleasure to see the way that people use the technology that people at Wolfram Research spend a lot of time building and trying to make as useful as possible. So I want to structure this talk on 3 basic areas. So the first will be talking about functions that automate a lot of the statistics and machine learning methods that one might be interested in doing. So in general, the design philosophy behind the Wolfram language that you use in Mathematica is to allow users to go into the options for being able to specify particular methods that you might be interested to do. Also to construct methods from scratch using low-level functionality. However, there are a lot of functions that are built into the language that make certain choices based off of what the data is like, or make certain choices based off of the size of the data set for picking a method and carrying out certain things in an automated way, so that if you are an expert in some domain area, but not necessarily an expert in particular methods and selecting the best ones, you'll get something sensible. And then the options will let you go and choose more detailed control over the algorithms that are used. So that's kind of the language design in this area. There's also functions for working with neural networks directly. And then during this part, one of the uses for neural networks in things like astronomy might be for synthetic data generation. So if you have a limited data set, but you're wanting to use machine learning techniques in order to expand this data set and then be able to use this larger expanded set for testing some pipeline that you're developing, this is sort of a common problem that comes up in many sciences, and astronomy is certainly one where this has found some use. And then the third topic that I'll talk about are using large language models from within Mathematica, and some of the things that seem to be most relevant for people who are doing science and might be interested in that functionality. So as just a prelude to talking about some of these things, remember also that there is a large built-in database of knowledge, which is the same information which is called by Wolfram Alpha whenever people are querying that website. So for example, here, what we're doing is we're creating a class of entities. So from the larger class of galaxy entities, we're picking ones only that have a shape of elliptical, spiral, or barred spiral. So this is excluding certain other types of shape classification. And then from this filtered down class, we're going to grab the image and what the shape classification actually is. We could also do this as well with the Hubble typology, rather than just the somewhat more vague shape classification, but for various reasons chose to do this one for this example. And so then we might want to select down. So for some of the examples you'll see using neural networks, we'll only be using things that are the RGB color space. And just to save myself a little bit of a headache in showing less of the image processing capabilities which are in the system, but which are kind of beyond the scope of what I wanted to talk about today, we're going to grab ones that are only of particular dimensions. And so a little bit later, after we talk about some of the functionality that builds in certain methods, we will synthesize some more images of galaxies based off of ones like this. So let's first talk about functions that are using techniques from statistics, or what one might call machine learning, either using some neural network or using what we might refer to as more traditional machine learning, things like various regression techniques. And these methods are automated, right? So of course, if we have data and we want to fit models, once you have one of these models, you can retrieve a lot of pre-computed properties of these. So you can fit nonlinear models as well. You can fit various distributions that are either parametric or non-parametric. So there's all sorts of functions that if you just have some kind of messy data and you want to automate the doing of statistics, there are these high-level functions that after you've found some fitted model, you can inquire from this fitted model, what are all the statistical properties that led this to be the model that was settled on given some sort of messy data set. And another thing that I didn't put too many concrete examples of here in the talk, but should be mentioned, is that one can also work with data that has uncertainties. And there's various guide pages for being able to look at that functionality as well. So, given all the various properties of models that one can compute, this allows you to, of course, make nice visualizations, which are another one of the things that we like to emphasize to people. Even if you're doing part of your data pipeline in other languages, and we'll talk about that in a moment, you might still want to bring that data back to Mathematica for either some pre or post processing, as well as the visualization capabilities, with which only a small amount of code you can make figures which look quite nice. Another function which uses various methods in an automated way is predict. So based off of what the data looks like, we might create predictor functions. And you see here, nearest neighbors was chosen as the method option for this. If we just say predict this data and we look at other method options, we see that there are various things that you can choose, and one of them is, of course, neural networks. Now, this is not a neural network that you'll have designed from scratch. If you choose neural network for one of these functions that has that as a method option, you'll get a network which is of some architecture, which is generally useful for data of the size and dimension that you're talking about. So the thing that we'll talk about during the second part of the talk is how you might roll up your sleeves and work a little bit more directly with neural networks. But I just wanted to call out that aside from these more traditional statistical techniques, you can, of course, select neural network as a method for working with certain functions. So, given this, we then might use this distribution that has been computed. And once we have a distribution, we can compute all sorts of statistical properties, and here show that this particular distribution, all of the data, except for maybe just a few, lie within 2 standard deviations of the fit line and what the estimated 2 standard deviations from this distribution are. And so this takes very little code. You're not necessarily having to worry about how do you calculate all of these things individually. This is, again, the language design meant to be very high level for doing some of these things, if that's what the user is interested in. Of course, one could recode all this from scratch, but you might not want to do that, right? You can use the higher level functions and then build things on top of that to accomplish things much more efficiently. So other functionality which is in the language is, of course, cluster analysis. And so here, the methods that one chooses really affect how the clusters are found. So here, this method is better for selecting clusters that have a different embedding in the space that they reside. Whereas here, if we were to use this same method on this clustered data, then of course we would wind up getting something that looks rather similar here. But then if we choose a different method option for this one, We'll just set the method to automatic this time. We'll see that we get different clusters because the automatic method was not the one that gave us what we might think of as the more natural clusters here, right? So the reason why I wanted to show this example briefly is just because sometimes the automatic method would be more or less what maps onto what you would hope you would get as a result of running a clustering algorithm. Other times you might have to, based off of your knowledge of where the data came from and the way that it's likely to be clustered, pick particular methods that are going to give you a more natural outcome from running the clustering algorithm. And of course, we can find communities in graphs. So this is other functionality that, again, very high level. You don't have to worry about method options unless you want to get down into the weeds on that. And we can also find components in images. This is used a lot in medical imaging, and so can also find some application to astronomical imaging. So dimensionality reduction is another area where one can select neural networks as part of the methods that are used. So here, we're not using a neural network, we're using an isomap to figure out, so given this data which is embedded in 3D but is really describing a two-dimensional manifold, we might want to find a dimension reduction that can put this same data into an embedding space that the data sort of naturally lives in. And so one thing that we might do is, so let's do a feature space plot after first doing dimension reduction on, so let's take from our cropped galaxy images, let's say 40 of these, and then let's set the methods that we want to use for our dimension reduction to an autoencoder. And this is something that we'll talk about in much more detail when we go into the part about neural networks specifically. And this autoencoder is going to find a dimension reduction function. Let me run that one more time, give it a name. So let's call this our dimension reduction function. And then let's do a feature space plot of these 40 galaxies. And for our feature extractor, let's use our dimension reduction function. And so if we run this, we've now taken these galaxies from whatever space this data lives in naturally, and we've reduced it to a two-dimensional space so that we can plot it. And based off of what you're plotting, you might find interesting patterns. We can see here that it seems that the higher redshift galaxies seem to be mostly clustered here, except for the ones which are, they might be more red in the image, but they're spirals, so they seem to be clustered up here. And so we'll talk in much more detail about how this autoencoder actually works, but this is a technique that might be quite useful for working with data, especially image data, where we find some representation of this data in terms of a vector space that can be of any dimension, but if we make it some dimension we can plot, you can use this to sort of visually parse things out. Another thing which is implemented at high level is anomaly detection. So here we might have some data. We train a anomaly detector function. And again, there are various methods for doing this as well. So here, this is done via kernel density estimation, but there are other methods that one can choose for doing it if you want to get into the weeds on specifically what method is most appropriate for your data. And then again, with relatively little code, you can use this detector function to be able to plot not only where the found outliers are given this anomaly detector, but also what the contours are for a rarer probability of data lying outside these contours would be quite rare, whereas the ones here are, according to this kernel density estimation, sort of at the middle of the parts of the distribution. So again, all of these techniques could be coded up from a much lower level, but we have these higher level functions as part of the language design to be more convenient so that you can write more efficient code and not have to worry about implementing those lower level details. Another thing which is, of course, quite relevant for working with real data is imputing missing values. So here is just some toy data set where we've intentionally removed all of the values that would lie here. And so what you can do is, again, there's various methods that one can use for imputing missing data, but we split the data into the ones that have missing. We train a function that can be used for imputing what are the missing values from the non-missing values, and then we can synthesize what we think the missing values should be. And sure enough, if you were to plot the data points that were from this initial data set before we removed them artificially, you would get something quite close to this. Real quickly before going into neural nets in more detail, we also have computer vision. So much computer vision is based in neural networks. And again, behind the scenes, there are neural networks here that are finding the images and identifying what they are. And many of them live in the neural net repository, which is something I'll talk about in more detail as we go. So from this repository, you can download various pre-trained networks. And one of the advantages of doing so is that you don't have to think about designing network architecture or training something from scratch. If you have a network that's been trained on some task vaguely similar to the one that you've are wanting to do, then frequently you can retrain only certain layers of that network in order to get some nice result. So semantic segmentation, so in other words, taking an image and finding what are the different parts of that image so that you can classify them is, of course, something that neural networks are used for quite a lot. And so if you want to find quite a lot of networks that have been trained, unfortunately, the neural net repository doesn't have too many that are trained explicitly on astronomy data, but that's perhaps something that we can change going forward because there are some interesting ones out there. And then I believe last but not least of functions that one might call more traditional statistics are things like signal processing, so that if we want to clean data with high and low pass filters, of course, this is, if we want to clean data with high and low pass filters, where here we're adjusting what the threshold is. This is, of course, something which is you're meant to be able to be done with relatively little code. And for those of you who do physics that or teach students who do physics that have audio as a domain, of course, many of these signal processing techniques can be applied there as well. I distinctly remember the chirps of gravitational waves back when those were first discovered. So that's an interesting, not quite audio, but one can think of it in much the same way. Okay, so now let's talk about neural networks more directly after going through some of that more wide-ranging functionality that relate to this topic. So what we want to do here is we're going to, through this example, we're going to build up a generator network that is part of what's called a generative adversarial network. And the purpose of this is going to be able to take these galaxy images that we have and create more synthetic data out of these galaxy images. So the original data set, if I look at the length of the raw data set that I imported, so there's about 10,000 galaxies that I grabbed initially. But then if we just look at the galaxies that are in that three-color color space in terms of their images and of the correct size, we have a much smaller number. So if you're wanting to do some training of a network to, let's say, classify them, you might want more images that aren't actually of real galaxies but are generated by synthetic that are synthetic data generated by some neural network. And so generative adversarial networks are one method to do this. There's a lot of other methods to do both this as well as solve other problems that come up in astronomy. And so there's a really, really nice review article that came out last year in which Smith and Geach talk about applications of neural networks to astronomy. And so I would strongly recommend anyone who's interested in this area to take a look at this article because I think it's a really great review article. Okay, so what are the building blocks of neural networks in our framework? Of course, neural networks are built out of layers. And so these are all of the different sorts of layers that you can find that are represented at a high level, right? So out of these layers, we build the neural network. So for example, you might be interested in defining your own custom layer that does something that isn't quite what any of these built-in layers are. We had some questions at the American Physical Society meeting back in March, where there was actually a user that was quite interested in defining some very strange loss function. So Euclidean distance is maybe a more normal thing that one might want to compute given some vectors. But there's a very strange loss function that he was computing because he was working on using neural networks to numerically solve partial differential equations in high dimension. And so because he wanted a very strange loss function, probably the best way to do it would be to set up a function layer in which you define whatever function you want to here. And this is not quite as general as just being able to use any function in the language. If you check out the documentation for this function, it spells out what the limitations are on what functions you're allowed to actually have as part of a layer in a neural network. And the reason for this is because the evaluation mechanism for a neural network is somewhat different than the rest of the language, especially because if you're wanting to parallelize things to GPUs for, let's say, training or evaluating a neural network, there's certain functions that aren't supported by this function layer, but many of them are. And so if you're curious in defining some special thing, you can. So then the layers of neural networks are then composed into what we would either call a net chain or a net graph. So what we might do is put together a sequence of, if we evaluate this, various layers. So let's just take a look at one of these deconvolution blocks, which we're going to have as part of our network. So let's give this a particular size so that we can have some concrete example. So let's say 256 and 8. And so if we look at what we have here, and then let's also maybe just take a look at the summary graphic. One of the things that people spend a lot of time in our framework making sure that people have access to are ways of understanding what the neural network is actually doing. And let's actually take a look at the full summary graphic. So here we see that each one of these individual blocks consists of taking the input and then finding some number of hidden channels specified by the little function that we've defined, and then convolving around each pixel up to some distance. And then in addition to doing that, we've got a layer that will then take only certain parts of that. We'll normalize the entire batch when we are going through training. And then the whole secret sauce to neural networks is that they involve some nonlinearities. So if we had no nonlinearities involved in training the networks, then everything would just be a very complicated and elaborate linear fit. And so, of course, that's not good enough to capture a lot of what we want to capture. And so at some point in your neural network, you'll need a layer that introduces these nonlinearities. So if we put a bunch of these together, we get a chain out of our layers. And then we might want to do the same thing where instead of having only a generator network, we'll have what we would call a discriminator network. And we can combine these into a generative adversarial network. So what the job of each of these things is going to be is, as inputs, we'll have an image. This will be one of either the real data set or a synthetic image. And then we'll also have some noise. So we have to decide what the latent space that we're trying to represent our data in is going to be. So here we've picked a 32-dimensional vector. And then given some noise coming from the space that we're trying to latently represent the data as, and the images, the job of the discriminator network will be to decide, did the image come from the real data set or did it come from our generator network? And then we can compute utility functions based off of how well the discriminator is able to pick out, is the image coming in a real one, or is it one that's created by the generator network? So in order to train this network, let's actually first go back to that autoencoder. You'll recall that the autoencoder was something that came up when we were doing dimension reduction before. So if we create an autoencoder and then we look at the summary graphic of this autoencoder, if we ignore some of the individual layers, so actually this is a good opportunity to show what the actual differences between just looking at a summary graphic or the full summary graphic might be. So if you look at the full summary graphic, you get to see layer by layer what's happening. However, you might come up with useful batches of what these layers are trying to accomplish. So the first part of the network is taking our input image and it's compressing it by doing some convolutions. And then we're taking that compressed version of the data and we're making sure that somewhere in the middle of the network, it's going down to a vector representation, which we get to pick whatever dimension we want. So here we're choosing 32 dimensional. For that dimension reduction that we did before, we reduced it down to 2 dimensions so that we could actually plot it. So something, maybe not this exact architecture, but something like this was what happened when we used that autoencoder method for being able to do the feature space plot of those galaxy images. So after we've squeezed the information down to some intermediate representation, then the intermediate representation is taken by the generator part of the network, and it's put back into the exact same format that we got out. So in other words, what we've constructed here is a very overly complicated identity map. Once we've trained it, so if we just put a bunch of random parameters here in terms of weights and biases for how the network should connect between layers, then it wouldn't be an identity map at all. We'd basically, if we make these just totally random weights and biases, it would be a map that is taking our inputs and just mapping them to some totally random other image. So the purpose of the training is to train this to be a identity map, or quite close to identity map, as close as we can get it with the training. And so things like the architecture of the network, the size of the network, some of the parameters that you choose for initializing the training, these are the things that are going to impact how good of an identity map this is. But the goal of an autoencoder is to be an identity map. And then after you've trained this identity map, you can sever the network here, and then you have something which will take, let's say, an image and then project it to some vector space. There's also what are called variational autoencoders that there's a link in the presentation to a very nice community post that talks about implementing those. So we'll talk about that in a little bit later too. Okay, so what we can then do is we might want to train this autoencoder, right? So here is what we would call a net graph. So notice in the previous example, this is a net chain since it just goes from input to output. Here, we take our input, we feed it into our autoencoder, and then the autoencoder is supposed to be an identity map, and then we compute the mean squared error by comparing what goes through our autoencoder with the original input to get our loss function. And then through gradient descent, we're going to want to do the usual thing of making this loss function as good as possible. So this particular thing takes about 10 minutes to train on the GPU on my laptop. So always remember when you're working with these sorts of things, do remember to export them so that then in other sessions you can import them later. And then what we'll do is we'll replace the untrained layers with the trained layers from our autoencoder. And then what this does is, so let's also show how this would work with some other galaxies as well. So I don't know, let's maybe do 110 to 119. So you see that what the autoencoder does is it's become pretty close to an identity map. These images are not precisely the same, and again, the exact architecture, size of the network, quality of the training set, all these sorts of things impact how good of an identity map it actually is. But the autoencoder, you can see, has basically succeeded in becoming an identity map, at least to reasonable approximation. So the difference between a variational autoencoder and this sort of autoencoder is that a variational autoencoder also incorporates some random noise into this process. And the advantage of doing that is that when you're using an autoencoder, as we're showing here, you don't necessarily learn a distribution in the latent space, which you can smoothly interpolate between. So sometimes that doesn't matter, but for certain purposes, you're going to want to use a variational autoencoder instead, because then it gives a distribution on the latent space, which is something where you can actually take two points in that latent space, and interpolating between them is somehow meaningful in terms of the original data. If you use this method of autoencoding, you don't necessarily get quite the same output. But at any rate, that's kind of beyond the scope of what I wanted to talk about, but you can read more about that here. So after we've pre-trained this autoencoder, this allows us to give our generative adversarial network a head start on its training. So what we do here is we replace the part of the autoencoder, which is the, we create our generator by starting with the generator from our autoencoder, which is now trained, and then the output should be interpreted as an image. Again, remember our discriminator network, its job is to look at an image and decide, is it something that came from the real data set, or is it something that was created by our generator network? And so here, we're taking the compressor part of the autoencoder, and then we're replacing that latent part of the network with just a simple linear layer that is going to mean that if we take a look at what are the actual outputs, so we feed in an image, and then what we wind up getting out is just a number, which can be interpreted as the probability that this is either the real image or the image that came from our generator. So now we have, instead of the generator and discriminator that had no initialization, we've used this autoencoding technique to give them a head start so that they're already a little bit better at doing their jobs. And then after we have this generative adversarial network operator, we call it, now we'll need to create a function that is able to get the data that we'll be feeding into this. So this is another thing that people were asking us about recently at the APS meeting, which are, let's say that I want to do some kind of Monte Carlo sampling, or I want to do some kind of non-trivial thing in between rounds of training my neural network. How can I do that? So what you can do is you can define a function that this function will have, in this case, some images, and then it will also be generating random latent data. So if we define these real quick, this is also another small network that we'll be using as part of generating our random latent space data. And then with these functions defined, what this does is if I run it, we'll wind up getting some galaxy images, and then paired with each galaxy image, we'll be getting some data, which is random noise according to some distribution that lives in our 32-dimensional latent space. So here's just a plot of the noise coming from the latent space that is going to be part of training our generative adversarial network along with these images that are the real things from our data set. And notice also, I want to call attention to, so some of the images in our initial data set have some artifacts for various reasons. And so you'll note that some of the images that our generator learns to create also are pretty heavy on artifacts. So what that means, practically speaking, is that the better quality data you use for training one of these, the better output you'll get. So then this generative adversarial network took about an hour to train on a GPU. The way that you make sure that this is functioning properly is you want to not only be training your generator, you want the discriminator part of the network to also be getting better. So through adjusting these parameters here, you can adjust what's the schedule for how many training rounds each one should take before having their weights and biases updated. Similarly, you can control the size of training batches and the training rounds. Again, if you choose not to specify any of these options, you'll get choices that should be sensible given the automatic options that we have implemented. But for certain things, you might well have an idea of what makes sense given your data. And so again, this is that high level where you don't necessarily need to specify these, but if you know something about your data, you might want to give particular values here. So now these that we get after we're done training the network is going to be something which none of these images are of real galaxies, it turns out. I think this particular one learned a much better job of creating elliptical galaxies. For whatever reason, because of artifacts in the training set, many of the spiral galaxies it creates does have some kind of artifacts, but there are some reasonable ones in here too. You'll notice this one was actually quite close to the artifacts that you were seeing in the one that I called out before from the real data set. There were some artifacts in the real data set where there's the foreground object that didn't quite get cropped out of the galaxy image, and so some of the artificially generated data has that same quality, right? So what one might actually want to do are train different adversarial networks for generating different kinds of galaxies. That might be something that one might try as well. So again, remember that you should export either to the ONNX file format or to Wolfram LanguageNet as something that is convenient to work with. Aside from generative adversarial networks, there's also various deep learning techniques that one might be interested in applying to astronomical data. So this is where we'll get back to talking about the neural net repository. So again, you don't necessarily have to worry about specifying networks from scratch. So one of the interesting things that one can do with neural networks is what's called transfer learning, where you take some network that was trained on maybe not even the same task. It could be just a somewhat related task. So some kind of identification task or something that in terms of the architecture of the network makes sense to try to transfer to the task that you actually care about. So here we have a network that was trained on images that are of a more terrestrial variety, right? So this one can pick out that this is in fact a particular bird. And this you can download from the neural net repository along with many other sorts of networks. But then what we might want to do with that is from this original network, if we look at what the original network was, let me re-download this real quick so that we can take a look. So if we look at the original network, you see this is a much deeper network than the ones that we were using for our generative adversarial network mini example from before. And so this network at the end, it's coming up with probabilities for 1,000 different classes that it might return as what it thinks the image is describing. So what we might be interested to see is, can I take this pre-trained network and not adjust anything in the first however many layers this happens to be until we get to the final thing, and then instead of having 1,000 classes, let's maybe just have 3 classes to determine if the galaxies are elliptical, spiral, or barred spiral. Remember that those were the 3 kinds of galaxies that I grabbed images of at the very beginning. So let's see how well this works. What we would do is we would use this net replace part function. We use that on the original network. And so what we'll do is we'll take this layer here that used to be size 1,000, and then we'll change what the classes that we're interpreting our final probabilities to mean. So once we've done this, all of these layers have their weights and biases from the original pre-trained network. And so if you're used to using train test split or similar functions from various Python libraries, do remember that we have a function repository that has many resource functions that can be used for these sorts of things as well. And so now this one took about 25 minutes to retrain since it was a fairly deep network. And so I won't do that live here, but the thing that you specify is that we don't want to touch any of the weights from any layer except for this linear layer that we've added. And you can tell it needs training because it's showing up here as being uninitialized, whereas the rest have values from the pre-trained network. So we set our learning rate multipliers so that only that particular layer will have its weights adjusted. We use nettrain in order to get a result. And so then after those 25 minutes, we have a retrained classifier, which will import here from having saved it before. And if we look at how that performed on the test set, so not the training set, we see that even with this relatively small number of training examples and using a network that was trained on nothing to do with astronomical data, right? So all the rest of this network just learned how to identify much more terrestrial objects. But in learning to do that task, it somehow figured out how to extract a lot of useful information from images. And so we can leverage that and see that even in this sort of not quite what the network was meant to do task, it's able to quite well tell the difference between elliptical as compared with various kinds of spiral galaxies. So in this little test that we did, that particular network was not very well able to learn the difference between spiral or barred spiral galaxies. And so almost all of the error comes from failing to distinguish those two classes as well as it maybe could. And so if we look at how well that it did overall, not very good. So transfer learning didn't particularly work on the entire task. However, it is interesting if you look at was the correct answer within the top 2 probabilities. So in other words, giving it a little bit of leeway here that it failed to learn the difference between these 2 classes in this small training run that we did. You see that actually the transfer learning worked reasonably well as long as you slightly move what you had in mind for the network to learn how to do. So even with a small example like that, hopefully that illustrates the concept of what you can do. And so I should also mention one of the things that we often encourage people to do is, it took far less time to write the code in order to do this than it did to train the network. And so even so, doing this retraining didn't take so long. So even if you're just wanting to do a quick prototype to see how well do you expect some concept to work if you want to scale it up, this is a very common workflow that we have in mind when we're designing the neural net framework. That possibly you might even want to use integrating your notebook with other tools. So I should mention as well that if you like to work in other languages as well, especially in the newest version of Mathematica, the ability to be able to use either Python, R, Julia, all sorts of other languages has gotten much easier even than it was in previous versions. And so a thing that people will sometimes do is you might want to prototype some pipeline really quickly, and then part of your pipeline, maybe you want to use some library that exists in another language, and that's a perfectly reasonable workflow that we try to support as much as people would like to use it. So that concludes the bit talking about neural networks. I hope that the application of synthesizing data was interesting to this group. You can of course do the same things with data that are in rotation curves, or let's say signals from pulsars. People have looked at that sort of thing of generating synthetic data, or training networks that can help them identify particular signals that they're looking for in those domains. But I thought the galaxy images would be a more interesting visual to go along with this talk. So last but not least, let's talk about tools for using large language models from within Mathematica. So one of the major use cases that one might find helpful are using large language models for code assistance. So a large language model is not one that you can run locally, hence the large part of it. So you would connect to various service providers. So companies like OpenAI, Anthropic, and Google all provide various model series. And so the first time that you go to use functionality like this, you'd be prompted for an API key from your service provider. And then,
So, sorry,
yes,
John. Sorry to interrupt you. So, I think at this moment, let us see if there are any questions from the audience, because before
sure,
going to the LLM,
sure.
if you have any question, please unmute yourself and you can ask. Okay, I think we may take up the questions at the end of your talk. So let us continue.
Sure.
Mm.
So code assistance, as I said, is sort of a major use case for working with large language models. And so let's say that you're working with particularly students. We find this is useful for. Uh, you know, let's say that you have some working code. So this is a problem in solid mechanics rather than relativity. But so if we have this code which is computing what are the stresses on a beam which is supported at one end, let's say, and we want to help teach someone new to the research group, or perhaps in a course, how does this work? The large language model can do a pretty good job of explaining what all of the different parameters in code are doing. So if you're looking at someone's notebook from work that they've done, and part of their code is written in a way that you find difficult to parse, large language models can be quite helpful with this. The other thing that they can do is they can, in addition to helping understand written code, is they can take a look at how to modify code that exists. And let me just get rid of that error message. So here we might ask just in natural language, what do you want to do in order to modify the problem in a particular way? And the language model is able to understand the code well enough to go ahead and reproduce the changes that we asked for in order to solve a related problem that requires being able to parse out what is each part of this code doing. Another thing that large language models can help with is data retrieval. So if we give them tools, then they're able to help us in finding various data which might be either in a knowledge base or which can be accessed through databases of other sort that you give the model access to. So here, let's say that we want to write code that generates a data set containing images and Hubble type for some galaxies. So one of the tools that's available to the models is documentation lookup. So if you want to have the model be able to write better code, it always helps to give them specifically what are the expected parameters of the code, right? So the language models do have a pretty good, a pretty impressive background knowledge, even if you don't provide them with these sorts of things. However, they do, of course, behave better if you remind them of specific things that are going to be relevant. So here, the language model has looked up what are the ways that you use these various functions. And the language model itself, of course, just sees plain text, but you might be interested to know in a formatted way, what is it looking at? And then given that it's able to look up documentation, it can then write you some code to help create data sets and perhaps do manipulations on such things. So there's also repositories for being able to create other tools for language models. A particular use case that we've been discussing actually is a tool for language models being able to help solve problems in variational calculus, because that's an area where the Wolfram language functions to do that are a bit obscure. Many people don't realize they exist, and so the language models don't do a great job of using their trained knowledge from all of their massive amounts of pre-training to set those problems up correctly. And so specific domains, the thing one might want to do is create a new tool that could specifically solve a particular problem type, and then give the model access to that so that they can, rather than having to write things from scratch, and because they have some stochasticity, you might not get the same output every time. We can instead give it a tool which is reliable, and the language models are pretty good at calling tools given the parameters that the users provided. So that's the quick overview of language models. If people have more questions about the language models specifically, I can go into much more detail about that. But I wanted to stop there and make sure that if we have time for questions, we can get to those.
Yeah, thanks, John. Nice representation of all these. I mean, I have just one or two quick questions. So,
Mhm.
I mean, although I am not an expert in this field, so this neural networks, etc., that what you have just shown us.
Mhm.
So, is there a possibility of doing? Doing research on the architecture side. I mean, if somebody wants to, change the architecture and see what is the performance of a particular network. So can one do that? I mean, tweaking.
Yes. In fact, let me bring up some examples of that. That might take me just a moment to find the one that I had in mind. But so if yeah, let me answer the question verbally while I'm looking for the specific example that I had in mind. So the basic answer is yes. Let's see. So let me find this on Wolfram Community. I think would be the best place to look. So we had a lot of projects at the Wolfram Summer School, which is another event that I would strongly encourage if anyone has graduate students that they're interested to find a summer research program. We have a lot of education programs where people study these exact questions. So let's take a look at, I think this community post that I'll bring up in just a moment. Yeah, so I'll reshare my screen now that I've found the correct one. So share. So this was, I think, my favorite project from last year's school. So this was taking a look at, can there be phase transitions in the behavior of large language models? Because there's this hyperparameter called temperature when you're using a large language model to figure out what is the next thing that it should say. And this analysis was done using one of the smaller models that you can actually run locally. There are a few such models. In fact, there should be a few more showing up in the Wolfram Neural Net repository before too long, aside from the GPT series, that you can, rather than sending API calls off and having to have a service provider to give you access to the language models, you can do experiments on something like GPT-2 or other smaller models locally. And so in other words, yes, there are a lot of really interesting open questions about why certain things of the architecture in neural networks are as useful as they are. A lot has been learned over the years. For example, this trick of compressing data to some smaller dimension than what it started as, and then taking it back to the same dimension that your input was in. In other words, what we just talked about with autoencoders, that trick shows up a lot in the architecture of all kinds of networks if you look really closely at what various parts are doing. Another really important thing that people are finding new uses for is the transformer block that goes into something like the models that are behind large language models. That can also be used for looking at certain sorts of time series data. And so people have used this for looking for signals. I believe in mostly gravitational waves, although I might be misremembering, and they've done that more so with other sorts of data. But at any rate, yes, there are certain architectural features of networks that people definitely still do research into to finding, are there more efficient ways of accomplishing the same task? So in short, the answer to that question is yes, that's still a very active area of research that people look into. I think that's a very specialist area. Although, of course, projects like this show that there's a lot of things about the operation of networks that physicists are in a very unique position to explore, right? Because physicists have tools from statistical mechanics and think about certain problems in a way that many of the people that design neural networks don't necessarily come from that training. I mean, it is always remarkable to me, like how many people that work in um, either data science or designing networks do have some kind of physics background. However, it is a somewhat different discipline, and so I think the time is very appropriate for people with an interest in physics to explore what's going on in the world of neural networks, and there might be some interesting cross-pollination that can happen there for sure.
Okay,
I'll
thanks.
go ahead and
Thanks a lot. Yeah.
put this into the Zoom chat as well. So other questions that folks might have?